Hey guys, Mr. O'Sullivan here. Hope you're doing well. Hey, welcome to 5 days to a Sixsky. This is day number two. We're going to talk about the derivative, uh, what the derivative is, and how we find it for different types of functions. Okay. All right. So first off, the graphical meaning of the derivative. Well, that's going to be it is the slope of the tangent line, or the slope of the line tangent to our function f of x at a particular place. We can also think of the derivative as a function. So it could be, it'll give us the slope of a tangent line anywhere on our function. The physical meaning of the derivative is the instantaneous rate of change. So it's the IROC, instantaneous rate of change of our function at a particular point. Okay, then we have two limit definitions of the derivative using the limit to define the derivative. First, as a function. So it's going to be the limit as h approaches 0. And our expression is basically just y2 minus y1 over x2 minus x1. So we've just dressed it up in function notation, f at x plus h minus f at x over x plus h minus x, which just simplifies down to h. And that gives us the derivative as a function, so f prime of x. The second limit definition of the derivative is at a point. That one's going to be similar. It's the limit as x approaches c, and then again the expression is just going to be the slope of a slope of a line between 2 points. So it's going to be y2 minus y1. This time it's going to be f at x minus f at c all over x minus c, and that's going to give us the derivative f prime, but at a particular x value that we're calling c. Okay. Derivative rules. Well, rather than have to use the limit definition of the derivative as a function to come up with our derivative, fortunately, there's a lot of derivative rules that we can use to kind of cut that process. But we want to make sure that we use the right derivative rule on the right type of function. Don't want to use a power rule on an exponential function, vice versa, that kind of thing. Well, we know a ton of derivative rules. We know probably the most important, chain rule, shows up everywhere. We know the power rule, constant rule, constant multiple rule, then we know the product rule. We want to find the derivative of a product of functions. We know the quotient rule that we use when we want to find the derivative of functions that are quotients, a function that is a quotient of other functions. And then we've got some trig rules and inverse trig. Let's go ahead and just run through those real quick. So the trig rules, so this is going to be ddx of all these, or ddx of sine of x. It's going to be cosine of x, ddx of cosine of x. That ddx is just going to go for all of these. That's going to be negative sine of x. ddx of secant of x is going to be secant of x, tan of x. ddx of cosecant of x is going to be negative cosecant x, cotan x. ddx of tan of x is going to be secant squared of x, and ddx of cotan of x is going to be negative cosecant squared x. We note again all those that begin with c, cosine, cosecant, and cotangent, their negatives, or I'm sorry, their derivatives are all negative. Okay. So those are the derivatives of the 6 trig functions. Okay. We also need to know the derivatives of the 6 inverse trigonometric functions. So here we go on those. So again, ddx for all these. Now it's going to be inverse, or arcsine. So ddx of arcsine is going to be 1 over square root 1 minus x squared. We'll write the d dx again. So we just understood for all of them. So then arc cosine. That one's easy. After we know that one, it's just going to be -1 over radical 1 minus x squared. d dx of arc secant can be 1 over, well, just because also as d dx of secant x was secant x tan x, this one's going to have a little bit more. It's going to be 1 over the absolute value of x times radical, and it's going to be x squared minus 1. d dx of arc cosecant is just going to be -1 of the absolute over the absolute value of x square root x squared minus 1. Then d dx of arctan of x is 1 over 1 plus x squared. No absolute value, no radical or anything like that. And then last but not least, d dx of arc cotangent of x, just like the others, it's just going to be -1 over 1 plus x squared. That's d dx of all those. Okay. All right. Now, derivatives of exponential. Well, if the base is e, life is good. So d dx of e is our base, e to the x, an exponential. Now, that's a beautiful thing. That's just going to be e to the x. Now, derivative of an exponential that's not base e is going to be d dx. Let's use 2 as our base, 2 to the x. Okay, well, that's going to be natural log of the base, natural log of 2 times 2 to the x. Notice in each case, when we take the derivative of an exponential function, the exponential function is part of its derivative. Okay, for e to the x, it's entirely the derivative. For a base other than e, 2 to the x, it's here. We also have this constant, though, natural log of 2. Okay. Okay. And then for logarithmic functions, same thing. We have d dx. Same thing, meaning that we see it one way if the base is e, and then we have a little bit more to do. We have a constant involved if the base is something other than e. So we have d dx of the natural log, that'd be log base e of x. That's going to be 1 over x. Now, if we have d dx of log base 3 of x, that's going to be 1 over natural log of 3, our base, x. Okay. If you remember change of base formula from logarithms, that might make sense to what we're doing right here. Because we could take this and use a change of base formula. We could say, hey, log base 3 of x is equivalent, if we want to change that into a log of another base, say natural log, that's going to be equivalent to the natural log of x over the natural log of 3. So then we're kind of back to 1 over the natural log of 3, which is a constant, times natural log of x. If we take d dx of all that, we can do constant multiple. That's a constant, just comes through 1 over natural log of 3, and d dx and natural log of x is 1 over x. So there you go. Either way you slice it, that's what we come to. Okay. All right. And then later on, after we started talking about integrals, we learned that there is another way that we can find derivatives, or actually we can find derivatives now of a new kind of family of functions. And those are functions that are defined as definite integrals. So that's FTC part 2. What's it do for us? It helps us find derivatives. Okay, well, this is what we might see it this way. Let's say that we have a function g of x, and it is defined as a definite integral. And let's say our lower bound is some constant. Now we'll use 2. And our variable is the upper bound, x. And then our function, let's say it is sine of t squared dt. Okay. And then FTC2 part, FTC part 2 comes into play when we want to find the derivative. And so the derivative of g at x would be g prime of x. And then what we're doing is we're taking the variable, the upper bound, and we're going to put it just right into our integrand, replacing the t. And so it's g prime of x is going to be sine of x squared. Now, we have to remember that if we have a situation here that's a little bit more complex, and let's say that we have h of x is equal to the definite integral 3, and we have say 4x squared is our upper bound, and then we've got, let's say, the natural log of t dt. And again, FTC part 2 comes into play when we're asked to find the derivative of this. So ddx of both sides, we get h prime of x is equal to, now here it's a two-step process. We're going to take, again, the 4x squared, go in place of the t. So we're going to have the natural log of 4x squared, but then we need to multiply by the derivative of that 4x squared, which is going to be 8x. So we have to remember chain rule on that. Okay. We had kind of a similar situation here, but when we took ddx of x, we just got dx, which is just 1, so we can ignore that. Okay. Derivatives of inverse functions. All right. Derivatives of inverse functions at corresponding points. Meaning if I have a point 2, 3 on one function, I know I have the point 3, 2 on the inverse of that function. At corresponding points are, how are they related? They are reciprocals. The derivatives of inverse functions at corresponding points are reciprocals of each other. Okay, so if our derivative is 2/3 at one point, it's going to be 3/2 at that corresponding point on the inverse function. Okay, higher order derivatives, we just need to make sure notationally we kind of understand. Obviously, we can show the second derivative, f double prime. We can also show it. There's our first derivative, dy dx. If we take ddx of that, this might help us. This is another notation for the second derivative. Okay. All right, let's go ahead and do some problems here. So if f is the function given by f of x is equal to 4 over x plus 5x minus 1, then f prime of 2 is equal to. Okay, well, first off, we're looking to find, whenever we're looking for f prime at a particular value, we got to find f prime of x first. And along that way, the rewrite, remember, the rewrite is your friend. So I'm going to rewrite f of x. I bet you can guess how I'm going to rewrite it. Solve this 4 over x. Ooh, you don't want to leave it like that and do quotient rule. What we want to do is bring the x out of the denominator. And so that's going to be 4x to the negative first plus 5x minus 1. Now, ddx of both sides. So f prime of x is going to be negative 4x to the negative second plus 5. And now I want f prime at 2. Negative 4 times 2 to the negative 2 plus 5. That's going to be negative 4 times 1/4, right? At 2 to the negative second, I'd write that as 1 over 2 to the positive second. So that's 1/4 plus 5. So that's going to be, oops, that's going to be negative 1 plus 5 is equal to 4. Please be an answer choice. Please be an answer choice. And it is. Okay. Not too bad. Bada boom, bada bing. Okay. So we're given y is equal to x squared times the quantity e to the x minus 1. And we want to find dy dx. Okay. So we're going to take d dx of both sides. So we're going to get dy dx, and we're going to have to use product rule. Okay. So product rule, we're going to have 2x times e to the x minus 1 plus x squared. And then d dx of that is just going to be e to the x. Okay. Now it looks like we've got to do a little simplification, a little algebra here. So I'm going to distribute that. So I got 2x e to the x minus 2x plus x squared e to the x. So now I'm looking, see if I can combine anything. And it looks like it's just the order's a little awkward here. So there's my x squared e to the x plus 2x e to the x minus 2x. C it is. Okay. Don't want to do the calculus right and then just kind of have a blip when we're selecting the correct answer. All right, moving on. So if f is a differentiable function and y is equal to sine of f at x squared, what is dy dx when x is equal to 3? Okay, so we're going to take d dx on both sides. Looks like we got chain rule. Looks like what, about 3 levels deep. So we should expect to have about 3 links in our chain. So I'm just going to take the derivative of the outside function. That would be cosine at f at x squared, right? So taking care of sine, now I'm moving in. So it's going to be then times the derivative of f is going to be f prime at x squared. And then I'm moving in one more. And then the derivative of the inside function x squared is going to be 2x. And now I want to know when x is 3. So all my x's that live in Texas are going to change into 3's that live in the trees. I'm going to duplicate that. I'm going to take out the x's and replace those with 3's. And then a little simplifying. We're going to have cosine, looks like, of f at 9 times f prime at 9 times 6. Okay. See in 6, f prime of 9, cosine f at 9. So D it is. All right, that was delightful. Okay, number 12, given that 3x minus tan y is equal to 4, what is dy dx in terms of y? Okay, we can just do implicit differentiation on this and just go d dx, left side just the way it is. I'm not gonna try to rearrange this and solve for y. I'm just going to do implicit differentiation just the way it is. So d dx to that side, d dx to the right side. I call the right side. That's going to be 0. d dx of a constant. So now on the left side, I want to be mindful. It's d dx, right? And I've got, so d dx of this first term, 3x, is just going to be 3 minus, now d dx of tan y is going to be secant squared y dy dx. That's chain rule right there, because I'm taking my operator's ddx and I'm taking the derivative of an expression in terms of y. Okay, so now I just want to solve for dy dx. I'm going to subtract 3. And I'm going to divide. So I got negative secant squared y dy dx is equal to negative 3. And now I want to divide by negative secant squared y. So on the left side, I get the dy dx that I was solving for. And then on the right side, I get 3 over secant squared y. Okay, quick look, I'm not seeing that. So there is a trig identity here. 1 over secant squared y is going to be equivalent to cosine squared y. So this is equal to 3 times cosine squared y. That's dy dx in terms of y. There it is right there. Okay. So did have to know simple trig identity there that 1 over secant is equal to cosine. Okay. All right. All right. Okay. This one here. Okay. So I've got d dx of the integral from e to x cubed of natural log of t squared plus 1 dt. Okay. As soon as I see d dx and the integral, I think FTC part 2. So I know what I've got to do is I've got to take that x cubed, plug it in for t in my integrand. So that's going to be x cubed squared plus 1. But then I've got to remember that I've also got to multiply by chain rule d dx of x cubed, which is 3x squared. Now I know I'm probably got a little simplification. So this is the natural log of x to the 6th plus 1, 3x squared. It looks like we brought that 3x squared out front. So 3x squared, natural log of x to the 6th plus 1. Okay, answer C. All right, moving on. Okay, selected values of the increasing function h and its derivative h prime are shown in the table above. If g is a differentiable function such that h at g at x is equal to x for all x, what is the value of g prime at 7? Okay, this one is it's a little tricky because we have to know what this piece of information is telling us about h and g. They're telling us that the composition of taking G, putting it inside of H, returns X for all X. So they're basically telling us in a roundabout way that what? H and G are inverses of each other. Okay. Sometimes in a problem like this, they'll come right out and they'll tell you. Sometimes they'll use this. They'll say H and H negative 1, or sometimes they'll say that, H, and then they'll say that G is equal to the inverse of H. So, either way, this way here is a little bit more subtle way of kind of just telling us that H and G are inverses of each other. But once we know that, what I would do is I would go back to my sentence there that derivatives of inverse functions at corresponding points are reciprocals of each other. So I'm going to just plot my two functions. I got H, I got G, and then under each one, I want to come up with my corresponding points. Well, the way I'm going to do this is I'm looking at, what am I asked to find? I'm asked to find G prime at 7. So I know that 7 has got to be an X value on G. So if that's the X value, I know that 7 is going to be the Y value on H because they're corresponding points on inverse functions. Now, what I want to find is, hey, what's the X value going to be on H? That's where I'm going to go to my table and I'm looking for the 7 that's the Y value. So that's it right there. When 7 is the Y on H, then 3 is the X value. So that's 3 there. That's 3 there. And now I know that G prime of 7, the derivatives of inverse functions at corresponding points are what? They're not equal, but they're reciprocals. So I know that G prime of 7 is equal to 1 over H prime at 3. Now I just have to go up to my table and I want to find a H prime at 3. That's 5. So this is 1/5. So G prime at 7 is 1/5. Okay. That one there, I mean, if you picked up on that they're telling you that H and G are inverses, it's not too bad. Okay. All right. All right. Moving on, moving on. So if dy dx is equal to that, then d3y over dx cubed evaluated x equals 2 is, okay, well, we just got to find the second derivative. given the first, and we want to get to the third. So we're going to go d2y over dx2 is equal to 4x to the third power rule. We could do that all day long. 6x squared plus 3, and then once more through the ringer. d3y dx3 12x squared minus 12x, and then we want that such that x is equal to 2. So 12 times 2 squared minus 12 times 2. It's going to be 48 minus 24, which is 24. Please be an answer choice. Please be an answer choice. And it is. Okay. All right. The rate at which water leaks from a tank in gallons per hour is modeled by R. Okay. A differentiable function of the number of hours after the leak is discovered. Which of the following is the best interpretation of R prime at 3? Okay. Well, let's see. So again, R is the rate at which water leaks from a tank in gallons per hour. So if we want R prime, that's going to be the rate of a rate. So I'm looking here, the amount of water, that's not going to work. The amount of change in gallons per hour, well, that's not going to be, I know my units for this need to be what? Gallons per hour per hour. So I mean, that's a good clue. Gallons per hour squared is what that needs to be in. So that's not right. B, the rate at which water leaks from the tank in gallons per hour, 3 hours. Nope. And then the rate of change of the rate at which water leaks from the tank in gallons per hour, 3 hours after the leak is discovered. Winner, winner, chicken dinner right there. Okay. Awesome. 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 Okay. All right. So the number of insects in a certain population at time t days is modeled by the function p with first derivative p prime is equal to that. At time t equals 0, the number of insects in the population is 40. Which of the following statements are true? Okay, at time t equals 10, the number of insects in the population is 2,840. 2, at time t equals 10, the number of insects in the population is increasing at a rate of 360 insects per day. And 3, at time t equals 10, the rate of change of the number of insects in the population is increasing at a rate of 18 insects per day Okay. All right. So let's be clear that P at T gives us the number of insects for some time T. Okay. P prime at T gives us the rate of change of the number of insects. And P double prime would be the rate of change of the rate of change of the number of insects for some time. Okay. Well, let's look at it this way. So let's look at Roman numeral 1. At time t equals 10, the number of insects in the population is 2,840. Well, how can we get that? Well, also, FYI, this is a calculator problem. So what I'm going to do with my calculator is I'm going to take p prime at t, and I'm going to store that in my calculator as y1. And then I'm going to find that so I'm going to find here the number of insects in the population is going to be given by the integral from 0 to 10 of p prime at t dt, but then I have to remember to add, they tell me here at time 0, we already have 40 insects in the population. So I'm going to have 40 plus that. And that I need to see, is that equal to 2,840? Okay. Roman numeral 2, at time t equals 10, the number of insects in the population is increasing at a rate of, well, that's just going to be p prime. So Roman numeral 2 is just going to be p prime at 40. I'm sorry, at 10 rather, time 10. Whatever that is, and I need to see if that is equal to 360. And then Roman numeral 3, probably guess what that's going to be. Time t equals 10, the rate of change of the number of insects in the population is increasing at a rate. So that's going to be p double prime at 10. See if that's equal to 18 insects per day per day. Okay, so let's see. I'm going to bring up my calculator and check here. I've already got that function in my calculator. So now I just want to check. Go out of there, go to my home screen. So 40 plus math 9 to bring up the integral from 0 to 10. It's in y1. 2,840. That checks. So that's true. Second one, I want p prime at 10. Okay, let's just basically bail out of that. I want that at 10, 360. That checks. So that one's true. And then lastly, I want to check, I want the derivative. So math 8. I want to take the derivative of p prime to get to p double prime at 10. That's 18. That also checks. So all of them check. So my answer is D. 1, 2, and 3. All right, that'll do it. Thanks, guys. Keep up the great work, and thanks for your efforts.